Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. I've introduced the abstract notion of an affine toric variety by using a cone and the corresponding monoid algebra. What I want to do in this video is to introduce the dual cone, because this is actually the way that you can easily record combinatorial information that's better suited for studying toric varieties. Okay, so to see how that works, let's just recall the setup that we have for abstract toric varieties. So we'll work with an algebraically closed field of characteristic 0, K. And now we're going to have to introduce dual lattices. Okay, so the first one, n. It's a lattice, so we might as well just fix it to be z to the n. And one thing that's a bit unusual here is that you have to work with both the integral and the rational versions. Okay, so what we'll do is we'll embed this inside n tensor over the integers q, which is just q to the n. So we have this lattice inside q to the n. And we also want to look at the dual group M. And this was the M that we used to define affine toric varieties. Okay, so this is going to be dual to this n here. So it's just the abelian group homomorphisms from n to z. So in particular, it's also isomorphic to the z to the n. And if we use the usual dot product, you can identify it with z to the n. Okay, so there's a pairing here, okay, from n cross m to z. So the pairing just works by, if you're given an element inside here, you can just apply an element of m to it to give you an element of z, and that's what you have over here. So that's the pairing on the integral level. There's also a pairing on the rational level. You can tensor both of these over q, which just means in this case, if you write the m and the n as z to the n, you just replace them with q to the n, and there's a similar pairing. And the pairing then has values inside the rationals, of course. Okay, so you're just taking the dot product of essentially rational n tuples to get a rational number. Okay, so where does the torus fit in all of this picture? It's good to know so that that's clear for us. Okay, so the torus here is going to be given by the homomorphisms from this m. Okay, so that's z to the n to k cross. Okay, and the homomorphism from z into k cross, of course, is just k cross. So that means that the homomorphism from m to k cross is k cross to the n. So this is just group homomorphism from here to here. And one of the things about the monoid algebra here, k of m, is that if you want to look at the k algebra homomorphisms from km to k, then that's the same as just in this case the group homomorphisms of m into k cross. So this is just also spec of km, and as I said before, this is the algebraic torus that's n-dimensional k cross to the n. So one nice way to write this is spec of km. Okay, and basically affine toric varieties you'll get from cones, and they will be gotten from some submonoid of this m. And so you get a sub-algebra of this, and you look at spec of that, and that means that this torus will be a dense open subset of that affine toric variety. Okay, so we need some simple definitions, and we're going to work inside the dual cone n, or its rational version, n tensor q. So we're going to consider a cone inside here, sigma, which is just some subset of this form. It's a sum of all non-negative q's times vi's. So you've got some set of vectors vi here, and you're taking non-negative rational linear combinations of those. Okay, the set of that. So that's some sigma, and we won't use this so much today, but an important definition is that for this cone to be strongly convex, it's strongly convex if suppose that you have a vector and it's negative inside here, then that vector has to be 0. Okay, so the only time you have a vector and it's negative inside here is when that vector is 0, for which of course this certainly holds, and anything of this form will have that 0. Okay, so let's just look at a very, very simple cone. So here I'm working inside the rationals, and so it is a rational cone, so to speak. Some people prefer to look at inside the reals, and you work inside real space, but then you still want all of these vectors to be rational, so to have rational coordinates, okay? So here I'll just work over the rationals like this. So here's a very simple example of a cone, and this cone is strongly convex. Its sigma is just given by non-negative rational linear combinations of the standard basis vectors E1, E2, and E3. So it's this purple region here. So this is the positive octant that you see in N1, N2, N3 space. Okay, this positive octant here. And that is a cone, and it's also a strongly convex cone. Okay, if you take the negative of any vector in here in this positive octant, you take the negative, it will be in the negative octant. Okay, and the only time when both of them are inside here is, of course, when you're at 0. So it's also strongly convex. Okay, so the next thing that we'll need to do is we need to look at the dual cone, and this will be something that's inside the dual, in this case, space. Okay, you were working in the rational space now, so it's inside M tensor Q. It's going to be the set of all vectors U here, such that the inner product or the pairing of U with anything inside sigma is going to be non-negative. Okay, so let's have a look and see what happens when you take a look at this cone, which is the positive octant, and you look at its dual cone, which will be inside M tensor Q, of course. So here the N was Z3. The M is also a copy of Z3. So let's look inside here. And what you'll find is that, well, if you want to have a non-negative inner product with every vector inside this positive octant, you just have to be inside the positive octant. So it looks the same like that. Okay. So in this case here, the calculation of the dual cone is quite easy to see. Okay, the next thing, and this is the key point about bringing in the dual cone, is to look at its faces. Okay, so the notion of a face is very, very simple. Its terminology comes from the faces of a polytope. Okay, so if you think of this positive octant as like some infinite polytope, you can talk about its faces. Normally you think of them as the sides, so they're the bounding hyperplanes. Okay, so there'll be 3 of them. Okay, but we want something that's a little bit more general than that. Okay, so let me state precisely what the face of some cone is. Okay, so the faces of the cone are themselves cones, and the cones are the following form. What you do is you take something in the dual cone, okay, U, okay, and that dual cone, of course, means that they're linear functions on this space, okay, and so you can look at it 0, so that's the hyperplane defined by it, U perp, and you intersect it with that sigma. Okay, that's what you're going to do. Okay, you're going to intersect it with that sigma. And then that will give you a face. Okay, so in what sense is it a face? So let's just do a little example so that you can really see. Okay, so it may look a bit funny, but when you think about it a little bit and see some examples, you realize that, oh yes, this is what you want to do. Okay, so let's pick something that's in the dual cone of here. Okay, so that's something, remember I said the dual cone of this is also just a positive octant. So I'm just going to pick 0, 1, 0. That's certainly inside there. Okay, so this is just the second basis vector. It just points in this direction, okay, towards me. And what I'm going to do is I'm going to look at the hyperplane corresponding to that. Okay, so it's a hyperplane, and you can use it to dot with vectors inside this 3-dimensional rational space. Okay, and when you dot with this, it just picks out the N2 coordinate. So it's going to be positive on this thing here, and of course it's positive on all of this sigma, because we chose U to be inside this dual cone. So it has to be positive on all of this, okay? So this U perp, it's going to be 0 here on the N1, N3 plane. It's going to be positive on this part, and it's going to be negative on this part there, okay? Negative on that part, but positive on this part here. Okay, so what you'll find is that when you intersect, right, this hyperplane with this cone, you just get this part here, okay, which is the intersection of the N1, N3 plane with this positive octant. So it's this positive quadrant in the N1, N3 plane. In other words, and it's quite easy just to calculate this, it's just going to be non-negative rational linear combinations of E1 and E3. if you have any non-negative rational linear combination of E1, E2, E3, and you dot with this and you get 0, that means that the coefficient of E2 is 0, so you just have some non-negative rational linear combination of E1 and E3. And then in that sense, you get a face in the usual sense of polytopes. Okay, so that's how you get some sort of a face. Okay, so that's the notion of a face. And one of the things that you would have seen is that if you look at this hyperplane, right, because this U was picked to be in the dual cone, the cone sigma is on one side of that plane, that hyperplane. So this hyperplane is also called a supporting hyperplane. Okay, this cone kind of sits on this supporting hyperplane. And where it intersects, that's going to be a face. Okay, let's look at a more interesting example. So I'm going to pick something else in the dual cone. That's this V, which is 0, 1, 1. So the 0, 1, 1 now points up like this. And if you look at what the supporting hyperplane, it's going to be like this. So you're going to intersect like this. And what you find is when you intersect, you just get this N1 axis, okay? Or rather the positive N1 axis. So when you intersect this sigma with this supporting hyperplane V perp now, all you get is just non-negative scalar multiples of E1. Okay, so this positive N1 axis. So this we still call a face, even though the dimension has gone down from something that was 3-dimensional down to something that's 1-dimensional. It's still called a face. And you may think, well, can you get something that's just 0-dimensional? Well, actually, if you have a plane that's not just tilted like this, but tilted back as well, then you can get just the 0. Okay, so that's also a face. Okay. But it's quite easy to sort of, when you imagine, right, supporting hyperplanes, right, and you think about how you can tilt it and keep this cone on one side, what are all the possibilities? The only possibilities are either the positive quadrants in one of the 3 coordinate hyperplanes, or the positive axes, either N1, N2, or N3, or the 0. So they're the possibilities for what the faces of this dual cone are. One thing else that I want to go through now is, well, why are we interested in this? Well, for that, I think it's good to have a look at the dual cones of these faces as well and see what happens. So we've looked at the dual cone of this sigma. Let's take this face here, which is given by this positive quadrant of the N1, N3 plane. Let's call that tau, and let's look at what is the dual cone of that. So they're the things such that when you take the inner product with or pair with anything in here, it's going to be non-negative. So certainly anything that's in the dual cone of sigma, because sigma is bigger than this, okay, is going to be in there. So you've certainly got this positive octant. But you'll note that actually, if you dot anything inside here with any number of E2s, the basis vector in this direction, okay, that's going to give you 0. Okay, so you can add any multiple of E2 that you like. So you can take anything inside here and you can shift it to the left or right. And it's quite easy to see. It's simple calculation. If you want to work out what is the dual cone of this face, you will now get something which is bigger than the original, the dual cone of the original sigma. Okay, so that's something you knew. And in this case, what it is you just take this and you just slide it to the left and right as you see fit. So essentially, it's something which, if you look at the N1, N3 coordinates, okay, you project onto this plane, it's in that positive quadrant, okay? So it's all the bit that's above this horizontal plane and in front of the back plane, okay, but you can slide to the left and right as much as you like. So there's something that's bigger than what you have. Okay, so let me introduce some notation here. So when we talk about dual cones, we can do it on the rational level inside here, and we can also do it on the level which is integral inside the n's and the m's. Okay, so firstly, n sigma, I'm going to use to mean just the integral version of sigma. So I just intersect this sigma with n. Okay, so remember sigma is inside here. Okay, it's in this copy of q to the n, which is n tensor q. Okay, so we can intersect that with n now. And then what is n sigma check? Okay, so I also introduced this in my previous video, but one nice way to sort of describe it is that you look at this sigma check here, this dual cone, and so this is in the dual space over here, okay, in the M tensor Q, and then you intersect it with this M. And if you follow this notation, since it's this intersection, it's just M intersect sigma check. Okay, so this M subscript sigma check. And this, of course, is again a monoid. Okay, so this is a submonoid, and this is a submonoid of this M tensor Q. Okay, that's a monoid, so it's a submonoid. And then you can use that submonoid to define monoid algebras. So this proposition is the key thing, which is kind of telling you why you want to look at the dual cone and the faces of it, okay? So suppose you consider a face of sigma, okay? Any face of sigma has the following form, okay? You just take some supporting hyperplane, so some u inside the dual cone sigma check. There's your supporting hyperplane u perp, and you intersect it with sigma, okay, and that gives you your tau. And so in particular, you can have a look at this tau, and now you go into the dual cone, you look at tau check, and you look at km tau check. Okay, this is this monoid algebra that gives you this affine toric variety when you look at the spec of this. So basically, the k points of this, remember, is just given by all the k-algebra morphisms of this into k, or in other words, all the monoid algebra morphisms of this into k. Okay, and so the natural question is, well, can you relate this monoid algebra to the monoid algebra given by the original cone sigma, k of m sigma check? And what's really nice is that, yes, there is a simple relationship between the two, okay? In fact, it's gotten by this just by localization. You've just inverted x to the u. So remember, u is inside sigma check. And so that means there's a corresponding element inside the monoid algebra x to the u, and its inverse is x to the minus u. And to go from here to here, okay, when you take the face, that corresponds to just inverting that x to the u. So that means that this is an affine toric variety corresponding to a principal open subset of this. And that's where you see the geometry of what's going on. So let me just highlight this because this is really nice, okay? Here you have a picture that describes for you a cone, and you have a face here as well. And the idea here is that if you take a face, okay, in terms of the corresponding affine toric variety, that corresponds to taking this principal open subset. Okay, so let me just explain briefly why this ought to be true. And the key point here is to show the following equality of rational cones. Okay, so if you look at this rational cone tau check and you want to relate to this sigma check, what I want to say is basically the relationship is you get this one from this one just by throwing in all rational multiples of u. Okay, so remember this u is already inside u check, so essentially you're just throwing in negative values of u as well. Okay, so maybe it's best to see a little example of this so that we can proceed. So here's your cone sigma, okay, and your dual cone sigma check is this positive octant. Then you have this tau that's defined by this 0, 1, 0. So that's the basis vector which is pointing over here like that. And what this little proposition is telling you is that this dual cone tau check is just gotten by, well, you take this original sigma check and you're just going to add in all scalar multiples of u, both positive and negative. The positive ones were already in there, okay? But now you're going to add the negatives ones as well. So that means that you get to drag this along as far back as you like. Okay, and that's what you see here. Okay, so to say roughly why this is true, let me explain that. So what is the left-hand side? The left-hand side is basically you take this tau check, you intersect with m. That gives you m tau check. That's the monoid. And then you get the monoid algebra for that. And I claim that essentially on this side, okay, if you intersect this with M, okay, and then you look at the monoid algebra of that, you will get this one here, okay. So that requires a little bit of checking, but it's hopefully highly believable for you now, because when you intersect M with this side here, what types of things do you expect to get? Okay, so you certainly get M intersect sigma check, which is this monoid here, okay, and U is already inside here, so the only things that you get are really extra bits from minus U, okay, so that's the extra minus U, so that's the only addition that you've really made. Okay, but to make this bit precise, you have to do a little bit of work, okay? So the more important thing I want to do is just to tell you roughly why this equality of the rational cones is true. Once you believe that, of course, you can intersect both sides with M, you get something, and then the only thing you have to do is to identify the monoid algebra that you get from intersecting M with this localization that you see here. Okay, so let's just see why this is true. Now, so firstly, it's true that the right-hand side is contained inside the left-hand side. Okay, so why is that? So this, remember, well, it's going to be a cone, okay? So firstly, sigma check is bigger than tau. Remember, this is a face. You got this by intersecting a hyperplane with this sigma, okay? So tau is smaller than sigma. And when you take the dual cone, it reverses the inclusion, because basically, if you look at what is the dual cone, it's going to be the set of all vectors u, which satisfies this condition here. So if you shrink sigma to a face, okay, there are few conditions to check. So since there are few conditions, it can only get bigger, okay? And we saw that happen here, as in fact, it will get bigger. Okay, so sigma check is inside tau check. And the other thing is that, well, u, when you take the inner product of u, okay, since tau is the supporting hyperplane, u inner product with anything inside tau is 0. So you can throw in any scalar multiple, positive or negative of u that you like, okay, and it's not going to affect your inner product with tau, so that's also inside there. So certainly this right-hand side is contained inside the left-hand side. And so the more interesting thing is, why is the left-hand side contained inside the right-hand side? And that's quite easy to see as well, okay. So let's just pick an arbitrary element w inside the left-hand side. And then what we're going to do is I claim that I can find some rational number a sufficiently positive, sufficiently large, such that if I modify this w by adding this au to it, this scalar multiple of u by a, the inner product, or the pairing with vi, so vi's were the basically the vectors defining this cone sigma, okay, so there's a finite set of them, this is non-negative for all I. Okay, so let me just try to show you why this is true. And this is a little bit technical, in the sense that you just have to go through the possibilities of what happens. But this is really explaining to you what goes on. Okay, so why is it possible that you can do this all the time? Okay, so you just have to show that for each I you can find such an A, and that when you pick a bigger A, this inequality only is easier to follow. Okay, so that's what you want to do. So you have to take cases where that VI, remember these VIs are inside sigma, and then so some of them might be in the face tau and some of them might not. So let's suppose firstly that VI is inside this face tau. Okay, so VI is inside this face tau. Remember, W is in the dual cone of tau, so that means that VI in a product with this W is greater than or equal to 0. Okay, so the other thing that you know is that this VI is in tau, so in particular it's in sigma. And remember, U is in the dual cone of sigma, so U in a product with VI is non-negative as well. And so if as soon as A is a positive number, okay, or non-negative number, right, when you do VI in a product of this, you'll be just adding non-negative numbers together, so you get something non-negative. So that's done there, okay? So the other thing that you want to do is to look at the case when VI is not inside tau. And when VI is not inside tau, okay, since this W is only in the dual cone of tau, you don't know whether this is non-negative or not. It could be negative. But now what you want to do is you want to pick the A so big that you can say that you can swamp out whatever negative term that you get from inner product of VI with W. And for that, you need VI inner product of U to be positive. And why is that true? So remember, U is in the dual cone. So certainly we have VI inner product U is greater than or equal to 0. But where is it equal to 0? The only time it equals 0 means that this VI is in the supporting hyperplane U perp. Okay, so VI would be in sigma and inside U perp then, which means that it would be inside tau. VI is inside tau, but we're assuming that's not the case. So VI is not in tau, so that means it's not in this U perp. Since we know it's in sigma, it can't be in the U perps. So the inner product with U has to be strictly positive, in fact. And that means that you can make this A big enough so that this will eventually be greater than or equal to 0. And that tells you that, well, you can find this A such that you have this inequality. But that means that this inner product of this W plus AU with any VI, with any of these VIs, is going to be non-negative, and hence with the whole cone it's going to be non-negative. So that means that W plus AU is actually in the dual cone of sigma. And that's in fact all you need to do, because that means that you can express anything inside this tau check, this W, as something inside sigma check minus that AU. Something inside sigma check minus that AU. Okay, and that gives you precisely this equality, and hence this proposition here. Okay, so just to sum up what is the main theme in this video, I've introduced the dual cone. Okay, so when you define an affine toric variety, you use a monoid algebra, okay, which is something like this. A monoid algebra, and you need a monoid. And that monoid is defined in some sort of space. But actually, even though that monoid uses a cone in a certain space, often it's better to use the dual cone to record the combinatorial information. And the reason why is that if you look at the dual cone here, so that's in the N here, right? The faces of this are going to give you the localizations that you really want to do, those torus invariant localizations, okay? So that really tells you about the geometry. And the other thing that's rather nice is that we saw, of course, that you can get lots of localizations of this form where you just invert by a single element corresponding to a monomial, okay? But when are they the same? Well, this proposition also kind of tells you when are they the same, okay? Because you can pick lots of different U's, okay? But sometimes they'll give you the same tau check, okay? And how can you tell when these localizations, these different localizations give you the same thing, okay? Well, it's telling you that you just have to look at these dual cones. And this is actually a duality. So actually, rather than those tau checks, you can just look at the faces. So basically, all the localizations that you're interested in, those torus invariant localizations, are just given by the faces of this dual cone. I hope you enjoyed this adventure in pure mathematics.